All right, good morning, everyone. Hope you guys had a good extended weekend. So let's get started again on what we were discussing last time. So we were talking about using multiple variables, multiple features to predict the target. So this is an extension from the last unit where we only used a single feature to predict the target. Now we have up to D features, x1 through xd. And we're doing linear prediction, which means we multiply each of these features by a slope coefficient, beta 1 through beta d, and then we also add an intercept term. So in total we have d plus 1 learnable coefficients, those are the betas in our model. And what we can do is we can stack them all into a vector, boldface beta, because that's a much more concise way of representing our unknown parameters. So our objective is to use our data set, which are these pairs xi, yi, where I goes 1 through n. And so these xi's, these are vectors of this form, where each of those vectors has features 1 through d, but there's also a subscript I here, right? So we talked about that over here. So this is the ith example of the feature vector. Okay, so we want to use our data to fit our parameters beta so that this model here approximates the data we have as closely as possible. Okay, so to set this up, we're going to do this two different ways. This is the first way. This way is direct, but not as interpretable. So the most direct way to do this is to collect all of our feature data. So the rows here are those boldface xi's. So this is like boldface x1 all the way down to boldface xd. But we're going to append onto this a column of ones. And the column of ones is there so that what we can do is we can write matrix A times vector B to give us our vector of targets. So just one note, when I'm writing by hand and I want to write a boldface quantity, I'm going to write an underline under it. And I suggest that you do something similar to that when you do your homework and exams so that you don't confuse scalars and vector quantities, because sometimes we'll have a problem where there's a vector quantity and a scalar quantity, and if I can't tell, or the grader can't tell what you mean, I can't give you full credit. Okay, so let's look at this relationship here. So if you look at the very first element in y hat, that's going to be y hat 1. That should be the very first element in this vector. So this vector here, to create that, I'm going to take, for example, to get the first element in that vector, I'm going to take this row and I'm going to multiply that times this column. So what that means, I'm going to get 1 times beta 0 plus x11 times beta 1, blah, 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 all the way to x1d times beta d, right? And that's giving exactly this for I equals 1. So the reason that I'm adding this column of 1s here is so that I can multiply this beta times those to recover this intercept term. Is that clear? This is where we're starting to use some of the linear algebra from the review. So the reason we're defining this feature matrix, or maybe you could say it's an augmented feature matrix because it has this column of 1s, is so that we can get a very concise expression for the vector of predicted targets. It's just A times beta. That's it. So are there any questions on this? Yes.
Question on the matrix itself. So
Yeah.
we defined X as a vector from like x1 to xd. So I guess what exactly is like x11 in that case?
Okay, so
Oh, okay.
so remember that there's sort of two dimensions to X. So the full X would be a matrix. And if you go down the rows, these are samples, or you could say examples of the data. As we go across the columns, these are different features that we're using to do a prediction. So, like if we're doing prediction of miles per gallon, we might be using horsepower as one feature and engine displacement as another feature and year of the car and all that stuff. So those are as you go across the columns. Yeah, so it's important to keep all these different things together in your mind. So yeah, the full feature data would be a matrix. If you want to talk about the ith example, then you take the ith row of that matrix, and that's what this is. Sometimes if you want to talk about just like the dth feature across all your data, you would actually take the dth column. And we'll see that come about if we want to find, like, for example, the mean of the dth feature. You would just take the average of all those numbers. Okay. So all we've done differently here is we've taken that feature matrix and then we've added the ones vector just so that we can make this very concise. All right. Any other questions? Okay. So this describes how we would predict the targets of our training. Maybe I'll sneak that in. These are the predicted training targets. What we really want to do is we want to make a model that we can use in the future for things outside our training data set. So if someone gives us a new feature vector, and let's call this x without any subscript, we want to predict its target, which we have no idea what that is. So what we're going to do is we're going to take our learned coefficients beta, and we're going to multiply it by a row vector that has the ones vector, and then I append on the right x transpose, which is a row vector, and then I'm going to multiply that times my beta. So again, what's happening here is that this 1 is going to multiply against the first coefficient in beta, which is beta 0. So that 1 times beta 0 will give me this part of the model. And then all the other coefficients here will multiply beta 1 through beta d, and they will give me this part of the model. Okay, so this is the training targets, and then this is a new target prediction. All right. Any questions? Okay. Great. So let's get into the details of how we fit those parameters beta to our model. So it's going to be very similar in spirit to what we did in the last unit, but just it's going to involve multiple different features now. So again, if I want to make a prediction of the ith training target, yi, I'm going to call that yi hat. Hat means prediction. And we know from before that this has the form beta 0 plus beta 1. And now I'm going to use the first feature, but the ith example of the first feature, xi1. And I'm going to do this for all the other ones up until I get to the ith example of the dth feature. Multiply that by beta d. So this is how I get my prediction of the ith target. And I want that these predictions are as close as possible to the data. And by close, we're going to make it close in the sum of squares sense, residual sum of squares. So we are going to define the RSS. This is the same definition from the last unit. So we have a sum over all of our examples I, yi minus yi hat squared. So the squared error should be minimal. And this beta dependence comes through yi, because as you can see, yi is dependent on all the beta terms. Okay, so we have a picture on the right which helps to explain what's going on. So this is going to be for the case d equals 2, where you have two features. So you'd have one feature x1, another feature x2, and as a function of those two features, so all your data points look like this. So these would be coordinates in 3 dimensions. So you have your x1 coordinate, your x2 coordinate, and your y coordinate. That gives you all these black dots. And this model here gives you the regression plane. So this is a plane as a function of x1 and x2. So as I move x1 and x2 around, I move somewhere on that plane. That's my prediction. So we could say this is like your y hat. And if you want to visualize the squared, or let's say visualize the residual yi minus y hat, those are the red lines. And so what we're saying is make the sum of the squared red lines as small as possible. Move the plane around until it's sitting so that the sum of squared errors is as small as possible. Making sense? Any questions? Okay, so last unit we had a line, now we have a plane. And this is a plane in 2 dimensions. We call it a hyperplane when you go to larger than 2 dimensions. It's difficult to visualize it because we are used to living in a 3-dimensional world, so it's hard to visualize more than 3 dimensions. But it turns out that all the geometry and all the intuitions you expect, they extend to any finite dimension. So we can draw pictures of planes even if the dimension is larger than 2, and we can use that as kind of a mock-up of what's going on in higher dimensions. So even though it's only d equals 2, it's representative of what happens for any finite dimension arbitrarily large. Okay. So now we're gonna work on this RSS, which here it is again, with a little bit more linear algebra. So the first thing we're going to do is we're going to write this as a norm. So what is a norm? A norm is a way of measuring the length of a vector. So there's different kinds of norms. The most common one is the Euclidean norm, also known as the L2 norm. And the Euclidean norm is distance as the crow flies, as we expect. So for example, on the right here, I have a picture this would be in 3 dimensions. So I have a vector x, and it has coordinates x1, x2, x3, and here's the origin. And so just the distance between those 2 points would be the Euclidean distance. And it's just from basic trigonometry. We know if we were living in a plane, the distance between 2 points, you could get that as the square root of the sum of the squares. And now when we're living in 3 dimensions, it's the square root of the sum of the squares again, but in all 3 dimensions. So this distance is square root of x1 squared plus x2 squared plus x3 squared. And that is, we can generalize that to any dimension d. Maybe I'll fill in. So there's j equals 1 through d. That's a general case. We sum up all our xj squared, and then we take the square root, and that is the norm. We write this norm with 2 bars. Sometimes when we want to talk about different norms, you might see someone put a little 2 in the subscript, and that 2 corresponds to this L2 or Euclidean norm. For now, you can just assume the Euclidean norm. Okay, so as you can see, now that we have this norm, when you look back at this expression here and compare it to the definition of the norm, it's very close, right? Like if I just would square the norm here, which would get rid of the square root, then it has this sum of squares. And so what we can recognize is that this RSS is the squared norm between the vector y and the vector y hat. Is that making sense from the definition of the norm? Okay. And now I can go one step further. If I want to describe this directly in terms of beta, I can expand y hat into the A matrix times the beta vector. And now you can see how exactly the RSS depends on beta. Okay, so this is a very common way to express RSS, and we'll use this as we go forward. Any questions on this? Okay. Okay, so let's just review a little bit, big picture. What we've done is similar to before and similar to what we'll do in the future. So general approach to machine learning. We start by assuming a model with some parameters. Here we've assumed a linear model with parameters beta 0 through beta d. We get our training data. In this case, our data is the form of pairs of vectors xi and scalars yi, and we have a total of n such pairs. We choose a loss function, which tells us like what really matters to us. We're going to choose sum of squared residuals. And the last step is find the parameters, in this case beta, that minimize our loss. So we want to find the beta vector that minimizes RSS. So this last step is what we have to work on a little bit more. So again, similar to what we did last time, but just in higher dimensions. We know that RSS is a quadratic function. So what do we mean? It means it depends on the beta coefficients or squares of those beta coefficients. In this case, the squares might mean like beta 1 times beta 2, but you'll never see more than two betas multiplying each other in a row. That's what it means to be quadratic. So let's verify that. So we start with our norm. Now, here's something to remember. I'm sure this was part of your linear algebra review, but if you have, I'll call it C. Let's just have a vector C, norm squared. We can write this as C transpose C because both of these, as you can see, look like the sum of C squareds, right? Whether I do it this way or whether I do it this way, they both mean the same thing. So if we want to simplify our norm squared, what we can do is we can write it as that vector transpose times itself. And now we have something in a more algebraic form, and we can multiply, we can expand this quadratic, so we get y transpose times y. That's the first term. Then we get y transpose times negative AB. And then we're actually going to have another one. There's going to be, maybe let's work out this term in more detail. So I have A, B transpose Y. AB, sorry about my bad handwriting. AB transpose Y. So if you remember, the way you apply transposes is you have to reverse the order and transpose the individual terms. So this gives us beta transpose times A transpose times Y. And we also have a minus. Okay, but let's also recognize one thing. What is the dimensionality of this final expression? Is this a vector, a matrix, or a scalar? let's think about this. So you start with beta transpose is a row vector, A transpose is a matrix, and Y is a column vector. When you're done with that multiplication, what are the dimensions? Scalar. Exactly. So this is a scalar. So what a transpose does is, transposes are usually applied to vectors and matrices, and they kind of flip the rows and the columns. If I have a scalar and I transpose a scalar, what happens? Nothing. So a scalar transpose is equal to itself. So knowing that, what we could do is we could write this, we could also, this is equal to itself transposed. And if I transpose this, I get Y transpose A beta. So these are the same. I can write things this way with the beta on the left, the Y on the right, or I can write things this way with the Y on the left and the beta on the right. It's the same thing. And this is all to explain to you where this term comes from. Because we saw that part of it came from this Y transpose A beta. That's one of these two. But the other one comes from the other cross term. So in total, you have two of them. Okay. As you get more efficient with linear algebra, this will be obvious. But in case it's not obvious, it's really important to figure this out now so that you don't get hung up on it as we move through the semester. Yes?
I didn't understand why the final dimension is scalar of B transpose A transpose Y.
Yeah. So this is a vector. This is a matrix, and then this is a vector. So let's just think about this first multiplication, vector times matrix. So what I'm going to do is I'm going to do this times this. That's going to give me one entry. That's this times this. That's going to give me one scalar. Then I'm going to do this times the next column, which is going to put another scalar next to it, and so on. And as I go to the end, I get, okay, so this part is a row vector. Now I'm going to multiply that row vector times a column vector, and I got a scalar. Yeah. Another way is just, if you just look at the dimensions, and you have a product of matrices. So first of all, you have to make sure that the matrices have the right sizes that they can even legally be in a product. Sometimes, you can write things down that don't make sense. It's impossible. It doesn't make sense. But in this case, everything is well defined. There's D coefficients here. There's D rows here. And then there's N columns here. And then there's N rows there. So everything works out. But if you just think about the dimensionality, the left dimension, the first dimension on this will be the final dimension here, and the second dimension here will be the final dimension here. And this is 1 and 1. So you're guaranteed to get a scalar. Okay, any other questions on how we got this middle term? Okay, and then the very last one, we have this times this. And here, this is going to be beta transpose times A transpose, and then just times A beta. Okay, so this is a way of multiplying through. And now you can see that this is a scalar term in beta. This is a linear term in beta. And this is our quadratic term in beta. And all together, when we add them up, we have a quadratic cost function. And that is why we get a shape that's going to look like this. This is in the two-dimensional case. Actually, it's in the one-dimensional case, you could say, because maybe you have beta 0 and beta 1. But like I said, the geometry extends. So here we have a parabola in 2 dimensions. As I increase D, I get parabolas in higher and higher dimensions, but they all, intuitively, they're all the same. You can always think of them as parabolas. That's enough. And what we know about these parabolas is that they're curved upwards. We're not going to really get too distracted by the linear algebra, but the way to say curving upwards in higher dimensions is you can say you build this matrix that's called the Hessian matrix. It's a matrix where you look at all the second derivatives, and then you analyze this and you check whether it's positive semi-definite. We'll talk about this in the future. And if it is positive semi-definite, that means that this thing is curved up. And if it's curved up, that's good because it has a minimum. If it was curved down and we want to minimize it, well, you just go out to minus infinity, right? That would be the minimum. But if it's curved up, then we're looking for the bottom of the bowl. That's meaningful. That's where our optimal beta coefficients live, and we're going to search for those. So this is the shape of the cost function. Our RSS is a function of beta. Here's another way of plotting this. So here we have contours. These are equal height. It's like a contour map. These are equal height slices. If you made slices through here, you'd get those ellipses. And here we're also plotting these gradient vectors. So the gradient is a very important quantity for us. It's the vector of partial derivatives. And what we know is that when you write at the optimum solution, the gradient vector equals 0. Whichever direction you look in, there's no slope. And so that's actually the mechanism we use to find the minimum, is we derive an expression for this gradient vector, we set it to 0, and then we solve for the betas that create that equal to 0 equality. It's the same thing we did in the last unit. Now we're just doing it with more betas than before. So again, the main point, any beta that zeros the gradient is a minimum. So that's our objective now. Here's the gradient vector. Let's compute the gradient vector and solve for the betas and set it to 0. Any questions before we move on? Okay. All right, so here's our, again, just to present it again, here's our RSS. This y hat I, this is a function of the different betas. And this aij, we are using that to denote the ith row and jth column of our A matrix. So I use this square bracket notation as we saw in the homework to extract rows and matrices of matrices or vectors. And I'm just defining that. Maybe I should have had a little triangle there. I'm just defining that as a lowercase aij. Okay, so we're ready to take our partial derivative with respect to the jth coefficient. In this case, j is any coefficient. And we're going to use the chain rule like before. So taking the partial derivative of this. So by the chain rule, the 2 comes down, and then I have to look at the derivative of this yi minus yi hat with respect to beta j. So this is a part I should explain a little more carefully. So let me rewrite this for clarity. I'm gonna call these j's j prime. I want them to be anything different than j, because over here we're holding j fixed. J is a very particular. J could be 0, it could be 1, whatever it is. It's a fixed number. It's the one we are taking the derivative of. Over here, j is being, now j prime is being used as what I call a dummy variable. It's just like a temporary variable that we use to do this sum. And as we know, you could expand this out to like ai1, or actually, even before that, we have beta 0 plus ai1, beta 1 plus dot, 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 all the way to aid, beta d. So when you think about this, we want to take the derivative with respect to beta j of yi hat, so of this. So when you look at it this way, what's the derivative of this thing I circled with respect to beta j? aij, exactly. So I'll write it here. D y hat I d beta j equals a I j. It's because there's only one term in this sum that has anything to do with beta j, and it's the term that has aij beta j in there. And when I take the derivative of that, that's easy. That's just aij. So what can get a little confusing sometimes is if you use j here as a dummy variable and simultaneously use j here, that means you're using j to mean two different things. And sometimes people get confused what's going on. So that's why it's a little safer to just rename this something else, j prime, and then to realize, oh, okay, I'm looking for one very particular j prime, which is j. And the j prime, which is j, that term is going to be aij beta j. And that's the one that gives me my non-zero derivative, which ends up here. Okay, so again, all of that was to try to explain where this expression came from. How did we get this part? Are there any more questions on this? Or is that pretty clear? We're going to be doing this a lot over the semester, so it's important to work out the questions now. So again, let me just do it quickly. So we're taking the derivative of this, with respect to beta j. So by the chain rule, we get 2 times the derivative of the internal part with respect to beta j. 2 times this times the derivative with respect to the internal part. The derivative with respect to the internal part, okay, we know that yi is not a function of beta j, so that goes to 0, the derivative goes to 0. And then we have the derivative of minus yi hat. And we saw that that is going to be minus aij. So here's our minus, here's the 2 from when that came down, and then here's our aij. Okay. So the next step now, and this is something you got a little practice on in the homework, is we want to write this back in the vector matrix world. So here we're in the summation world. We want to write this equivalent using matrices and vectors. So this is something that takes a little bit of practice if you're not used to doing this. But so this sum is actually equal to this, to the jth element of this quantity. For me, it's a little bit easier to start from here and say, if I wanted to express this matrix vector multiply in terms of the summation, how would I do it? I would do it like this. So I would look at the jth row of A transpose, and then that row would be multiplying this column vector here. So the jth row of AI transpose has these terms here where I goes from 1 to n. So there's a little bit of mental gymnastics because of the transpose. But the transpose, essentially what it does is it flips the order of the two indices, exchanges rows for columns. So another way to say it is, if you want to view what is the index that's coming across the columns of that matrix, that's the index I, and that's the same index that's the same index that's coming down the rows of that vector, right? It has to be the same index. And then the index coming down the rows of A transpose, that is J. And this is flipped. Usually the A matrix without the transpose, you have I down the rows, J across columns, and now when we put the transpose there, it flips the I and J. So this is the full matrix. If I take the jth entry, that means I'm just looking at the jth row here times this entire vector, and that gives me exactly this. Okay. Any questions on this? Yes?
Why don't we just get the partial derivative of RSS and the vector beta, and then wrap the J entry?
Yeah. So the question is, can't we just do vector calculus?
Yeah.
And the answer is yes, if you know vector calculus, you can do it. So part of what I'm trying to do in this course is teach vector calculus little by little. So I think many people probably don't know the vector calculus yet, and so we're just taking small steps to get there. But if you know vector calculus, then yeah, you can do the derivative directly and use that directly. Okay. Okay, any other questions? All right. So the very last step is if we want to write this expression as a function of beta, then we can plug in a times beta for that y hat term, and now we have an expression where you can see exactly how the derivative of the RSS depends on beta. And remember, we want equal to 0 for j equals 1 to d. Actually, 0 to d. Sorry. Because we start with beta 0. So we want that this derivative, this is the jth component of the gradient, right? We want the entire gradient vector to be 0. That means all the components should be 0. So if this expression for all j equals 0, then that means that this entire vector equals the 0 vector. So that's where we get this. The 0 vector, this is a vector of all zeros. That's why it's bold. 0 vector equals this. We just now have to solve for the beta that causes this to happen, and that is our solution. That's our least squares solution. Okay, so this is relatively easy. We multiply through, we get A transpose Y times A transpose A beta. We then move the A transpose A beta to the left side, and we get this. And the last thing we need to do is we need to write this as, we need to move this to the right side. Does anybody know how to do that? How do I move this over here? Inverse. I take it left inverse. In other words, I multiply both sides of that equation by A transpose A quantity inverse. And when I do that, I cancel the A transpose A on the left, and I get A transpose A inverse A transpose Y on the right. Okay, so multiplying the left side of both quantities by A transpose A, that will cancel this one, leaving beta least squares, and it will produce this on the right side. Now, in doing this, I have assumed that this matrix is invertible. Not all matrices are invertible. I'm assuming this one is invertible, and we have to be a little bit careful. If we have more features than data examples, what happens in that case is our matrix A actually is wide, and this A transpose A will be what we call singular. It's not invertible. So we're going to assume that it is invertible just to be simple for now, but we will talk about lack of invertibility later, where this could arise and how to deal with it. But for now, we'll just assume the simple case where you have tons of data, not too many features, you can invert this matrix and you get your least squares solution.
I was going to ask what the LS means, but it's
Oh,
least squares.
yes, that's right. LS is least squares. Okay, so this is, sorry, my handwriting is not so good there, but this is our least squares solution, our least squares fit. Okay, any questions on this? All right. So similar to what we did in the last unit, you could ask the question, well, how good is our fit? And in fact, this slide is exactly the same as the last unit, so I won't spend much time on it. The first thing to remember is that RSS on its own, it's not as clear from this expression, but you saw it last time. RSS is going to grow proportional to the number of samples in our data set. So that dependence on n is a little bit annoying. It would help if we just divided RSS by n so that the resulting quantity does not scale with n. Similarly, RSS grows with the scale of y, with the variance of y. So that motivates us to divide RSS by n and the variance of y. The resulting quantity is a normalized quantity, and it's very nice to deal with. So now typically, rather than looking at that normalized quantity, you look at 1 minus it. 1 minus RSS divided by n divided by, sorry, we called this s y squared, and we define this as r squared. So this is exactly the same as the last unit. And we discussed last time how when r squared equals 1, that's the best that can possibly be because that means the RSS is 0. That means you have perfect prediction. If you find that you get r squared equals 0, that means that the predictor you have designed is no better than the trivial one. You can also get r squared equals 0 simply by setting yi hat equal to the sample mean of y, in other words, y bar, for all I. So that would be a very trivial predictor where you just completely ignore the features altogether, and that gives you r squared equals 0. It is possible to do worse than trivial, maybe if you make a mistake in your coding, but hopefully you're not doing that. And if you have the least squares predictor, it should always be between, somewhere from 0 to 1, never negative. Okay. All right, so again, same exact slide as last time. Now, the expression that we just derived is not very intuitive. When you look at it, you see there's a lot going on. Number one, this matrix A, not only does it have the features in there, it has this column of ones. Number two, it appears 3 times and transposed and not transposed and inversed. So it's kind of hard to get a lot of insight when we look at this. So the question is, can we express this instead using the sample statistics of the data, which is something we were able to do with simple linear regression? In other words, like sample mean, sample covariance, things like that. And the answer is yes, we can. We just have to extend our statistics from scalar to vector. So that's what we'll do next. Before we do that, we're just going to rewrite our model in a notationally tiny bit different way. So this is the model we've been using all along. And what we'd like to do is recognize that the first coefficient behaves a bit differently from the rest, in that the first one is the intercept and all the other coefficients are slope coefficients. In other words, all these guys multiply x's and the first one does not. So because they work in different ways, let's partition our beta vector into the first term and the rest of the terms. And the notation I'm going to use for the rest of the terms, I'm going to use the boldface beta, but then in the subscript, I'm going to put 1:d. That just means beta with coefficients 1 through d. In other words, leaving out coefficient 0. So with this slightly different way of expression beta, now our predicted value y hat would be the intercept plus all the slope terms times the feature vector. And this is going to be convenient as we go forward. So just rewriting it a little different. Okay, any questions on this? Okay, so now let's briefly talk about sample statistics again, but what are the sample statistics when we have a vector? So let's start with the sample mean. So let's say I have a collection of vectors xi, where I goes through 1 through d, and I want to know what's the sample mean of that data set. Well, it's defined the same way as before. It's just the average of all those xi's. But just remember that these are all vector quantities. So that means the average is also a vector quantity. We'll call it x bar, but now x is boldface to tell us that this is a vector. And it turns out, if you think about this, the very first term in this vector x bar is actually the scalar sample mean of the first feature as you go across your data. Right? So these are the scalar sample means from the last unit, and when you stack them all together, you get the vector sample mean. Okay, this is a scalar sample mean of our targets because right now our targets are still scalar. Nothing's changed. Okay, slightly more interesting one is how would we generalize the variance? So here at the bottom, we have the variance as we defined it in the last unit. So in that case, we had a scalar features. So we had xi, scalar, and we looked at xi minus x squared, basically. Sorry, xi minus x bar. We're going to do exactly the same thing now, but we're going to use these vector quantities. So on the left, we have a column vector. On the right, because of the transpose, we have a row vector. What happens if you multiply a column vector times a row vector? What do you get?
A square matrix.
Exactly, a square matrix. This. So this term is an entire matrix. It's not a scalar, not a vector, it's an entire matrix. And this, as you can see, I wrote it with a capital boldface to remind us that it's a matrix. So we call this the sample autocovariance matrix. Sample because we're just taking an average of the samples. Autocovariance is the name given to this kind of structure. So it's a extension of the variance, but now it's like a matrix valued variance. Similarly, we have sample cross-covariance vector. So here we have our vector valued quantity, and on the right we just have a scalar. When you multiply vector times scalar, we just get a vector. So over on the left here we have a lowercase boldface to remind us it's a scalar, and then the xy subscript reminds us that it's the statistic of multiplying the x's times the y's after removing the means. And that one is very similar to the cross covariance that we saw in the last unit, where we had scalar valued features. Now we have vector valued features. Okay, so now that we have our statistics defined, we can move forward and work on a derivation where we will get a more intuitive expression for the least squares prediction. But are there any questions on anything here before we move forward? Okay. Well, yeah, we have one more thing to do. Sometimes it helps to rewrite these in a slightly different way. So from the previous page, this is how we defined the sample autocovariance matrix. And if we expand this, this is like first terms, and then we have the x bar times xi gives the second term, and then we have xi times x bar gives us the third term. Finally, x bar times x bar transpose gives us the last term. But we can simplify. Let's look at this. Do we recognize what this is inside the parentheses there? We have a name for that. What is it? You guys, x bar, exactly. It's the sample mean of the x vectors. Same expression arises here. So now you can see we have x bar transpose, that appears once. X bar transpose appears twice, appears 3 times. First 2 times have negatives, second time is a positive. So basically this all boils down to minus x bar transpose. So let's just write it like that. Minus x bar transpose. So this is another way of writing the autocovariance. And we can also write the cross covariance in a very similar way, we multiply out this, we distribute this, so we get xi, yi, we get x bar yi. When we do this, you can see that we have y bar here, sample mean of y, and then we get the xi y bar, which is this, but this gives us sample mean of the x vectors, and finally x bar y bar, like this. And again, the last three terms have the same form, but the first two times it's negative, the last time it's positive. So altogether, we get 1 over n times sum of I going to n of xi yi minus x bar y bar. Okay, and these expressions will be useful in the next few slides. Okay. Any questions? Good, all right. So finally, we can do this derivation. So similar steps to before. We want to set the gradients with respect to the different betas equal to 0. But we have to treat beta 0 differently from all the other beta j's. So this is our RSS expression here. We take the partial derivative with respect to beta 0. That means that some of this stuff has no dependence on it. This is easy. So we're going to get a minus 2. This is because of the 2 here and the minus here. And we're going to get a sum. I goes from 1 to n. And then we're going to get what's in the parentheses. And that's it. We're going to do the same thing for the derivative with respect to beta j, but now we have to be a little bit more careful. If you're not completely fluent with your linear algebra, let's write out this term here. So I'm going to use j prime. Again, this is a sum over j prime going from 1 to d. I'm going to have x I j prime times beta j prime. And using the prime there is helpful so that we don't confuse it with the j that's over here. So to take partial derivative with chain rule, I'm going to get 2 times this whole sum times the derivative of this. And you can see the first two terms go away when I take the derivative. And when I take the derivative of this sum with respect to beta j, there's only one term that matters. It's when j prime equals j. And at that point, what's in that sum is just xij beta j. We take the derivative with respect to beta j of that, we just get xij. So finally, we get minus 2, do this simply, minus 2 times the sum, I equals 1 to n. We're going to get xij, and then what's in the parentheses there. Okay. Any questions on how we got that expression? Everyone okay with that? Okay, good. And so now we just basically have to solve these two expressions for our betas. It's not too difficult. We'll actually use the same steps as the last unit. So the first thing we're going to do is multiply both these expressions. Actually, multiply this one by minus 1 over 2n, which is going to turn this into a 1 over n. So that's going to give us this. And once we expand this, we can see this is the sample mean of y bar. This is the average of the beta naughts. That's just beta naught. And then we have this average of these terms. So we have average of the xi transpose. That's just x bar transpose times beta 1 to d. So this equals 0. The last step is move the beta naught to this side, and you can see that it exactly equals y bar minus x bar transpose beta 1 through d. So we don't yet know what the beta 1 through d is, but if we did, we would know exactly what beta 0 is. So the very last step, which we'll do on the next page, is to figure out what is that beta 1d. Once we know that, we'll be done. Okay. Any questions on this page? Okay. All right, let's finish this up. So this is our second expression from the previous page. We're going to multiply this by minus 1 over 2n, and that's what gave this 1 over n. Now we can expand this out. So we have this first term over here. We have, this is going to be the average across i's of the jth feature. So that's going to be x bar j times beta naught. And then we have the average of xij's times these things. So that is going to be this over here. Okay, so before we move on, let's take this expression here, equation 3, and plug that in for here. So that is going to expand this term to those two. And last step is to realize, okay, this is what's happening when I took the derivative with respect to beta j. This whole expression is a scalar. Can I identify this as the jth entry of a particular vector? And the answer is yes. So let's look at this term. This is the jth entry of this. So it's like you take the entire xi vector and multiply by yi. That the jth entry of that would be there. The jth entry of this would be this. The jth entry of this would be this. And finally, the jth entry of this would be this. And what's nice about this last expression is these are all recognizable quantities. In fact, does this one look familiar here? What do we call this one? That's SXY. Exactly. SXY, the vector. And then on the right, we have beta 1 through d. That's a common term here. And if you look at this, XX transpose minus this, does that look familiar? Turns out that that is minus matrix SXX times beta 1 through d. And, sorry, maybe I should move this a little closer. Okay. And this again is just, we're looking at the jth entry of this quantity. But we don't really care about what's happening in the jth entry. We want this to be 0 for all the entries j. So that means this entire vector must be 0, which is summarized here. The 0 vector equals this vector. And now we're almost done. We move this to the left side. We get SXX, I'm sorry, there should be an underline, beta 1 through d equals SXY, which implies that beta 1 through d equals SXX inverse SXY. Again, assuming this is invertible. Assuming invertible. Okay, so basically what we've uncovered now are two expressions. The first for beta 1 through d. This is written in terms of the statistics of our data. And once we know that, we can plug that into here. We get an expression for beta, again, written in terms of the statistics. So I think this is a good time to stop. Sorry I went a little bit over. We'll pick this up next time and take a closer look at these expressions and compare them to the ones from the last unit. Anyway, have a great rest of your day, and I'll see you guys on Friday.